So hello everyone and welcome back to the daily late code practice session. And we'll be going through three problems: easy, medium, hard. And let's get started. So for today's problems, the first problem, which is from easy bucket, is symmetric tree. Has anyone tried or has any approach for this one? Or do anyone want to explain what the problem is? Hey guys, am I audible?
Yes, you are.
Yes, you are audible.
Okay, I thought I was speaking to myself. Yeah, so let me share my screen. Okay. So here's the first problem for today, symmetric tree. So we are given a tree as an input, and what we have to do is find out whether that tree is symmetric or not. And by symmetric, what they mean is if you consider this 1, 2, and 3, 4, 3, 3 servers. So if you draw a vertical line at the root, you will find the mirror images of all elements on both the sides, right? So if you have a element over here at 1 in between, you'll find the 2 on each side. And if you have a mirror in this line, you'll have 4, 3, 4, and 4, 3. Okay. Now, if you go to the other one, and if you try to build a vertical wall here, at the first level, you'll see that 2, 2 is a mirror image. But if you see at the other level, it's not exactly mirror image. It's the same format. Like if you have, suppose you had a left child called as null, the mirror image would have been null 3 and 3 null, but it's not the mirror image. So this one is not a symmetric tree. Is the problem clear?
Yes. Yep.
Okay. Has anyone tried this? Any approach, any ideas, what to do, how to do?
Yeah, I've tried to solve this problem, but recursively I was thinking to compare the left and right subtrees. So let's say we start for the first tree, let's say we start at 1, and recursively we'll check whether the two childs, left child and right child, are equal or not. But this fails in case like on the third level. So because for again for first 2, which is on left, 3 can't be equal to 4. 3 has to be equal to the rightmost 3.
Okay.
The right child of the like 2. So that is what we want to compare. So recursively to compare that, I don't know how to check the value from the sibling and how to proceed.
Okay. Anything which you think, is there any way which you think you will be able to compare the first and the last element and the remaining ones? Any idea that comes into your mind?
Actually, we want to compare values on the same level actually. So that we can do by level order traversal. Again, if we do level order traversal of this tree, so on the second level 2 is equals to 2, and again on third level if we do level order traversal, so we get exactly like the string which we get or the numbers which we get are exactly the palindrome 3443, that is the property, and if it is there then it will be a symmetric tree.
Correct. So that's one of the approaches, like you can do a level order traversal, and at each level you can find whether it's a palindrome or not.
Yeah.
But that will fail for your second case if because that was also a palindrome.
Yeah, I'm coming to that. What will happen in this case?
Yeah, that will fail actually. Yep. We are interested in the position as well, not only in palindromic string.
Correct. Does this input format give you any idea about if we can use the palindrome feature?
This is a pre-order input, na? 1, 2, 2,
Yeah,
nine.
I'm not saying the exact value, but I'm just saying the format in which this input is given. Can we use some idea from this input and try to have that pre-order approach or the level order approach implemented here also?
Puneet is asking you to look at the null and think about it, I guess.
Correct.
Or maybe we can substitute something like add a zero instead of a null in the string and then check whether it,
Your voice is not audible. Could you just speak a bit loud?
I'm saying that maybe like in the list of like the string that we're generating to check the parameter, we just need to check like on the level the left half is equal it's the mirror image of the right half or not. So that we can do by substituting instead of a null maybe something like a value or a placeholder kind of a thing in the string and then check on the level because on every level we know the number of nodes so we can check this half equal to that half.
Right. So instead of having null not represented in your level order traversal, you may substitute null with any character which is not in the tree. Let's suppose a dollar. In that case, your level order traversal will be $3 and $3. So can you now try and see whether you can create a palindrome?
Actually, this input thing is interesting because each level has 2 raised to power n elements. So, like 1, then 2 elements are at second level, then third level will contain 2 raised to power 2, like 4 elements, and it is starting from null 3, null 3. So this is not a palindrome on one level. So from here we can see that this won't be a symmetric tree. Am I closer?
Right, that's correct. So this is just a representation of tree. The input that is given to you is not a tree. It's actually a root of tree, right? So this is one of the ways lead code usually provides input in for the trees. If you see, this is a structure which is generally used by lead code for an input of tree. If you
Okay,
try to visualize it, you'll see the first node is always the root, and then you have corresponding children with them, the next two elements. And if they are one of them is null, it will explicitly light it as null, so that it's a one-to-one serialized. So they can directly serialize and deserialize it from that string. So I was just trying, if you can take the idea directly from that.
Okay.
So if we could replace the nulls here with something like dollar and then do a level order traversal, the initial approach that was discussed was take each level, try to find the entire string and see if it's a palindrome.
Yep.
Right? Then that makes sense. Yeah, that approach is fine. What will be the time and space complexity for that?
For level order traversal, it will take linear time to visit all the elements and linear space as well to maintain a queue.
That's correct. So any other approach?
Just a minute. Actually, in previous case, we were also checking whether it is a palindrome or not. Now, suppose your one level has n elements. You can only get O of n, like palindrome check is, you have to spend O of n time just to check whether it is a palindrome or not. If you do it for each level, so you are doing it out for so many times, it may
It
become
will
O of
not
n
be
square.
essential. It will be n log n, right?
N log n, yeah.
The height of the
Yeah,
tree will be log n.
yeah, height of the tree is 1 log n. So let me think. So 1 plus 2 plus 4. So you have this geometric progression, right? So because first level is just one element, second is 2. If you continue doing that, you have 2 to the power n minus 1. Like, yeah, so those many. Yeah, you can say that. Yep.
Right. So it will be n log n time complexity. That's correct. So any other approach where, probably we could reduce the time complexity, or any other approach where we don't have to compare at level and do something else?
My thinking, I think I will have 2 pointer, one one move to the left and one move to the right at the same time. So kind of like one would traverse pre-order on the left side, and the other one would traverse what they call reverse pre-order. So I can compare them. So for example, I go from the first one, I go the 2 pointer point to 1, right? And then the next time, the left pointer point to 2, and the right pointer point to 2 on the other side.
Okay, so you're saying reverse in order, right?
Yeah. No, reverse pre-order. I mean, one going to pre-order,
Correct.
and the other one going to reverse pre-order. And, at each move, I compare the value.
Right. Let me check if there's if it will create any other cases. Like, let's suppose we have root as 1, we have 2 at the left, and okay, so you're saying pre-order. Let me share my screen. So let's suppose we have this 1. Here also. Then we have 3, 4, and 3. So let's try to see if we can create another pre-order traversal, which will give us the same output, right?
Okay.
Let's see if there's 2. Let's keep the right one as is. So here pre-order traversal will be 1, 2, 3, and 4. That's correct.
1, 2, yes.
So is this a valid pre-order again?
No, but when I traverse, I also have to compare the node too. So, so let's say for the second example, the left child of 2 is no, but the right, the right child of 2 on the other side is 3. So it's not the same.
Okay, so you're trying to compare from the left child, every left node will be equivalent to right node.
Right.
On the other end. Right, so we can do that. If we have this 3 and then there's 4. So what we are doing essentially is trying to compare for each child, left child of this one will be equivalent, it should be equivalent to right child, and the right child should be equivalent to the left child.
Right.
Let's go a level further. We have 5, 6, 7, and 8. And then we have 8, 7, 6, and 5, right? Now suppose we have done with this level, we know it's same. And we are now here, we are trying to compare whether it's, it creates a symmetric tree or not, right? So what will happen now? What will we compare? The last 2 ends or the first 2, or what will we compare?
The 3 on the left side and 3 on the right side.
Right.
Right. And now the next one will compare the 5 on the last level, left side, and the 5 on the right side.
Right. So essentially what we are doing is at every node, we are comparing its corresponding entry on the right and its left with left node on the left with right node on the right, correct?
Right.
So, okay. So if we try to create a, recursive relation or recursive property using this, could we do that?
Yeah, this is kind of recursive, right? Because I do on the left side, it will be pre-order. But let's think about if we traverse the tree on the left side, the pre-order, what are going to be? It'd be 1, 2, 3, right? And then when on the right side, we do reverse pre-order, and then we kind of can compare them. But in this case, I do recursively.
Correct. So if you see the pre-order, it follows a pattern of you first visit the root, then you visit the left child, and then you visit the right child.
Right.
Right. And if we do a reverse pre-order, it'll take the
root,
right child,
right, and the left,
and then left child.
Yeah.
Right.
Right.
And if you compare it with how you are comparing right now, isn't it similar? You're first comparing the root, and then comparing the left child with the right child of the other side.
Right. Yeah.
Right. So if we find a pattern, or if we find a way to traverse both the trees at the same time, one in pre-order and one in post-order, and compare each of those, we are done with the problems, right? So let's say here we start with node 1, right? It's a single node, and then we can take the 2 childs that we have. Are they equal? There's only one, yes, they are equal. So we are done with that. Okay, and till this level, it's similar. Right? We are done with, if we are going on the left child, it's going to follow the pre-order, and this one will be reverse pre-order. Right?
Yeah.
Now what we have to do is take left child of this one. Let's take it's 3. And for the other iteration, we have to check right child. Are those two same? Yes. Let's move ahead. From right child, we'll see 4. From here, we'll see 4. Right? Both of them are same, right? Now, what we'll do, instead of comparing these only at this level, we'll also insert them in some sort of a queue where we can take up the next elements to compare. Let's assume that queue is here. Right? And we know once this level is done, we'll have to compare this element with this element, right? The children of these elements with children of these elements, this element, right? That's what you're, checking on the left child symmetry and checking on the right child symmetry means.
Yeah.
Correct? So what we'll do is, while we're comparing the values, we'll also insert them into a queue. We now know we have to compare 3 from the left child, 3 from the right child in the next step. And similarly, once we are done with these 2 in this level, right, next 2 will be 4 from the left child and 4 from the right child. Once we are done with each level, what we can do is take the top 2 from the queue and try to expand them. Right? And the same approach goes. Now we have 5 and 5, which will be compared first. If they are equal, we'll put 5 in here. 5 from left, 5 from right. Next step is 3 has other childs. Right child of 3 will be 6, 6 from left and 6 from right. So everything is equal till now. We are in the symmetry. Now suppose we hit a situation where we don't have the left child of this one, and there's only right child. So now based on the condition, it should have symmetry. There should be, both of the children should be there, which are not there. We can stop here and return false. So this is not a symmetric. But at any stage when we are processing and at the end we see there's nothing left in the queue to process, that means we have processed all the nodes and all the nodes are symmetrical. Does that make sense?
Okay, yep. So here we are like not comparing the palindrome. So this complexity would exactly be O of n.
Right. So what we are doing here is, instead of creating a palindrome and checking, we are traversing it from the ends only, right? From the 2 extreme ends, and then trying to come in between. So essentially, if you are traveling in this way in the pre-order and this way in the reverse pre-order. So if every element is same, that is essentially your palindrome. And you'll not start your next level till the current level elements are done, right?
Okay.
That's how BFS works.
So just by changing the insertion into the queue, we have achieved that. Like pushing into the queue, the sequence of insertion we have changed so that this can be achieved, because we are
Exactly.
inserting
Exactly.
in a
So we are
normal
not inserting in this way. We are inserting from the two different ends.
two different ends. Okay, yep, understood.
Any other questions? Guys, is this clear? Any questions? We
Yes,
can
it's
discuss
clear.
them. Otherwise, we can move forward. Okay, so I'll assume it's okay. And let me share my screen again to discuss the next problem. So the next problem in today's bucket from Medium is convert a sorted linked list to binary search tree. The problem is very self-explanatory. So we are given a linked list which is already sorted. And what we have to do is convert it into a binary search tree, but that should be balanced. And by balance, what do you mean is the difference between the depth of two subtrees, right, should not have difference more than one. So it's a very generic definition of a balanced tree. Like if you have these trees like 0, -3, 9, 10, and 5, each node, let's suppose this one, has a balance difference of 0. Everything is 0. There's no child. So it has balance difference 0. It's a valid balanced tree till here. Now coming to -3, you have one left child, 0 right child. So it's still having a balance property fulfilled because the difference between the left and right child is 1. Same goes for these two nodes and the 0. So 0 has a maximum depth of 2 from left hand side. On right hand side, it also has 2. So your root is also balanced, right? This tree entirely at each perspective, as each node's perspective is balanced tree. So same thing we have to do is to convert this sorted list into binary tree now, binary search tree now. Any approach, ideas?
Yeah, actually, binary search tree is simple. Like we have to find the middle element, and then recursively we have to call for left subarray and right subarray to be created. Like that is the first approach, but that works like quite well with arrays. But this is a case of linked list, and to find the middle element here, we have to like traverse the linked list and find the middle element, because we don't have any index based access in this case. So that we can achieve here.
How will you find the middle element for the linked list?
Straightforward, like brute force approach would be to no, one approach is to pass the linked list twice, to traverse the linked list twice. In first pass, we'll calculate the length, and in the second pass, we'll go till n by 2, the length by 2.
Okay,
In
so
that way,
now
we can.
suppose the linked list is very long. Is there a way we can do it in a single pass?
Yeah, to do it in a single pass, we have to have 2 pointers. One will take, basically one is slower pointer and the other one is fast pointer. Fast pointer will take 2 jumps and slow pointer will take 1 jump. And till the time we'll reach the end by the fast pointer, we have to check whether the next element is null or the next is null. So if this condition breaks, so our slow pointer is at middle element. So
Correct.
this is the approach. Yep.
So what will be the time and space complexity for this one?
To find the middle element here, the time complexity would be O of n. And space would be O of 1 constant space. We are not using any space here. Auxiliary space we are not using, we are only traversing. So this will work in O(n) time.
How would you create that tree? Will you not use any intermediate stack, like even the function stack?
Okay. Apart from this finding middle element, the existing problem, yep. To find the middle element and then call recursively for 0 to mid -1 and then mid +1 to length.
Right. And how much space would it use?
Recursion would like implicitly stack would use O of n, like what would be the height log of n that it will use, I think. Extra space that stack will be filled.
And from the time complexity point of view?
From time complexity point of view, it will take linear time O of n, because we are visiting each element once and
okay, so you're visiting each element once, but at each level you're also trying to linearly check for the middle element, right?
So that becomes n square. Yeah, that becomes n square, I think. Yep. That is.
Anyone else? Everyone thinks it's n square?
I guess it would be, we can use an array also and just, yeah, we can store the elements in array. And then the time complexity would be big O of n, as we are visiting each by computation, each element once.
Okay.
So the time complexity would, space complexity would be big O of n, and time complexity also would be big O of n.
Right. So that's what if you convert it into a array, right?
Yes. And by indexing, we'll be going to the middle element of the. We'll be doing it recursively, I guess.
Right. And the approach that we are discussing till now, what will be the time and space complexity at that time?
What would time and space complexity? We aren't using any array or something.
No, if we are directly converting from sorted linked list into a tree.
Into a tree. Okay.
Right.
But how would we going to the middle element actually? Because otherwise we'll be just reshifting the elements of the arrays.
Yeah, that's what I think we're just discussing.
I
for
think
a linked list.
I think that we we know the size of the linked list, right? So let's say if we know the size of the linked list and we build the tree or node from left to right, then we count the number of nodes we build. So by the time the count equal to length over 2, we know that node is a root node.
All right. So let me share my screen. I think I'll help to understand, explain what he's trying to say. So we have this array, right? Linked list. Correct? If we can do one pass and find the number of elements, we know there are 5 elements, right? Your first element will be at index 1, your last element will be at index 5. Just assuming that there's index from 1 to 5. Now we know where middle element will be. It will always be at, right? So middle element, which is 3. 5 plus 1 divided by 2, which is 3. So third index will be your middle element, or the third position element. You can directly take this 3 and find the third element, right? And then everything before that and everything after that will become your left and right child, right? Now, if you are doing it a left child, or going on to a left child, your head or left child will have indexes from 1 to 2 only, and your right hand side will also have from 4 to 5. But now let's, remap this problem to base condition. Now your head in this condition will be something pointing to 1. But when you go to the right hand side, your head will change to 4 and 5. Right? I'm just passing the head of the linked list also to the next iteration so that they can understand from where to start. Now coming here, this one is 1 to 2. We can remap this 4 to 5 index again to 1 to 2. And we again know if we divide 2 plus 1 by 2, which is simply 1, we know the first row index will be our next root. So we can take that one, right? So this one, this will be our root, and the remaining part will go to the next level. Is this understood? So what we are doing at each level, instead of solving the problem for a bigger linked list, let me just change the values. So 5, 7, 10, 12, 15, and 16. And these are indexes 1, 2, 3, 4, 5, and 6. So what I'm doing is essentially when I'm at here, this position, I'm just trying to find out what will be the middle element for this one, right? Now I know it will be, suppose 3. I'll take this one, set it up as root, and now I need to know what is my left child and right child, right? I know I have to process 1 to 2 index elements here, and I have to process 4 to 6 indexes here, right? When I was processing this part, I knew the head was at the 5th position. Now coming to the left child, what I'll do is I'll again pass this array, but now I'll say I have head at 5 and 7, and then there's something which will never reach because I'm already only processing 1 to 2 elements, right? And for the right part, what I'll say is there's an array, its head is this one, right? 4th element. So you have 12, you have 15, you have 16. There are some before that, but this function which is going to get processed, it will never have reference to anything before that because the head pointer will start from here, right?
Hello.
Is this okay till now? Yeah.
So you are assuming that you have a 2 head pointers, like a head 1 will be a start from 5 to 7 and head 2 will be a start from 12 to 16, or it's the same pointer?
It will be 2 different pointers, right? So assume a function which does what? It just takes the head and finds the root and then calls itself again with the new points. So your input state will change every time. Your head will change, that will give you a new. And what additional input I'm saying it, you have to only process 1 to 2 elements for creating. So essentially, even if you pass this entire array, the effective array for calculation will be only this part. Right? And if you go to the right hand side, I have to just, for some way, I have to make, make this part of function believe before this one. And how I can do that is just point the header to this position. Yeah, there's no way a pointer can go back, right? Linked list cannot do back traversal. So for this part of the function, the linked list is this much only. Does it make sense? So effectively what we are doing is, starting from this header, this part is going to process only two elements. And starting from this header, this one is going to process 1 to 3. If we normalize this or, re-index this to 1, it is going to process 1 to 3rd element, right? And we again know if we have only 3 elements, 1 plus 3 by 2, second element in this will be a root. So I'll set up 15. Anything which was starting from this node, just give me a second. Yeah. So going from this initial index, I can directly go back to what is pending, like 12. And whatever is my root, the next pointer to that will go into the right one. Now, when I am processing this one, I can see there's only one element, and that will be the only root. I don't have to process any further. Same goes for the left part. I'll take 1, 1 as the root here. Left one will also pass the same pointer, but it will pass the number of indexes to process as 0. Because we are at the first index and there's nothing before that, right? There's no element before that. So it will pass and there's will be nothing created. Now from the right hand side, we'll have one element, which is 2, 2, right? This indexes will change from 1 to 2 to 2 to 2, because I'm just processing that one element. And now it will create a 7 here and all the tree is complete. Does this make sense? Any questions here? Or any other approach anyone has tried?
So what would be the complexity of this?
This approach, right?
Yeah, it should be something related to log n.
Right. So let's see how many elements we are processing at each level, right? Let me just clear a bit so that you can see it. Okay, so we have 10 here, and then we have 5, 7 in this side. We have 12, 15, and 16 on this side.
Yeah.
And then when I'm splitting it again, I have 5 this side. Sorry, there's no element here. I have 7 this side, right? And then coming here, I have 12 this side, 16 this side, right? Right. So once here, I am doing the n by 2 scan,
Which is log n. So,
no, n by 2, because if I know the length 6 by 2, to find the middle element, I need to scan it. It's a linked list, not a array,
yes.
right? So I have to go by n by 2 element times. Now let's assume this size is n by 2 and this is also n by 2. That will be the worst case, if just one element is removed, right? Now this will have to do an n by 4 scan here and n by 4 scan here, right? The length in by half.
Yeah.
And this will be a geometric progression, right? And it will tend to 0, right? Now, can we calculate what will be the number of elements here? So essentially, worst case scenario will be, we'll be comparing each level and have those, all the n elements be compared somehow. If there's only 2, we'll have n by 2 this side, n by 2 this side, n by 2 this side, and then calculate for n by 2. This will be done twice. So it is essentially n by 2. Now here we'll have, at worst case, we'll have one element here, one element here, one element here, one element here. So the number of times we are splitting, like it will be n by 4, will also create that many branches, right? So we'll have n by 8 into 4. So again, n by 2. So at every step, we are doing n by 2 computations. And we know the height of this one will be log n. Right?
Okay. Even after splitting it into multiple branches, we are doing n by 2 calculations at each level. This is what you are implying.
So at first level, when we know the length is 6, to find the middle, we have to traverse n by 2 elements, right?
Yeah.
At when we have length as n by 2, how many times we'll have to iterate to get the middle? N by 4, which is essentially n by 2 divided by 2.
And there are 2 subtrees.
Right, and there are 2 subtrees, which will essentially give us back the n by 2 as the value.
Okay, yep.
Right. At every step, we'll have n by 2, n by 2, n by 2. And we know how many levels it will create, because it's a binary search tree. It will create log n number of times, right? So we have log n. So n log n, again, the time complexity for this one. Right? And from the space complexity point of view,
it's still a recursive solution, so it will take that stack and it will fill log n elements into that. So O of log n.
right. So we have this binary search tree, log of n, which at some height will be the stack space that it will do, function stack space it will use, right?
Because we are implying that it will be a height balance tree, so we can't consider the case of skew tree. In that
Right.
case, it will
That's
be
what we
first
have to
place.
create. That is why we are trying to position it the middle element as the root. Right. Otherwise, we can use this array and create n number of trees from this. We can use this one as root. We can use this one as every one of those can be a root. If we are not concerned about the height balancing.
Okay.
And they will all be a valid binary search trees. Right?
Hey Puneet,
Yeah.
I would like to also offer another way to look at time complexity, just to it may be useful in other scenarios. So
Sure.
what we essentially are doing, suppose Tn was the time complexity for the overall problem because we had n nodes. We do two things. We do a O of n check to figure out the length. That is one task we do. And after we perform that, we reduce the problem in two halves. So we can call Tn is almost equal to O of n plus 2 into Tn by 2. Is that clear? If you can write it, maybe it will make sense somewhere. So if you erase or you find a space where you can write,
Okay. So
it wouldn't take long. So
you
yeah,
can try.
yeah. So write Tn is equal to 2 into Tn by 2 because now we have two problems of half length plus O of n because we were calculating the mid element, and we know that we are going to do it for height is like log n times, right? So basically, if you derive this, eventually you will have same complexity, time complexity, if you are familiar with how to solve these simple
So
equations.
this, yeah. So there's something called as Master's theorem in calculating task time complexity. So that essentially deals with these kind of recurrent solution, how you can find the final complexity for this.
Yes, yes, that solves a lot of problems. This is a simpler one, so you can just exactly do what we just did. But this is a very common one, so just by looking at it, you see that we are halving at every level. So, and we have such log levels. So clearly in log n. Yeah, that was alternative way to derive that. That's it.
Thanks, Roger. Any other approach, any other ideas, thinking process for this problem? I know there was a very interesting way of solving this problem in one of the discussions in the code, but I have not gone through it. It's something based on in-order traversal. Probably if you get time, I will share that link and just go through that. It's, I think, in the solutions already, not in the discussions. That's a very interesting problem to play with all the indexes.
What did they use? Sorry, I didn't get a chance to look at it. What did they use?
So they were, trying to simulate so it was something like if you have 1 to 5 indexes, and if you try to simulate a in-order traversal, you will know the next left or 3 will be the root here, and you will have 1 to 2 elements here, and 4 to 5 elements here. Now let's go back again here. If we split this one, divide by 2, you will have 1 comma 1 here, and 2 comma, will not have 1. If you make 2 root here, you will have 1 comma 1 here. Now, when you reach at this stage, so you are in the leftmost node, leftmost root, right? There's only one element. So at this time, go ahead and use the first element from the linked list.
Oh, I see.
Create a node. Now you'll come back here, right? And then now you have traversed everything on the left. In the in-order traversal, this will be the next node that needs to be created. So take the second element and create this one. And then for the remaining ones, just process the right one, right side. So when it's back from here, you'll definitely have all the node pointer penned to something which is going to be the next element.
So this
So
is O
instead
of
of
n, I guess.
actually taking the yes, O of n plus again the space complexity will be log of n.
Right. Good. Nice.
Instead of actually taking the array and taking it out, we know the property that binary search tree will produce an inorder traversal which is sorted. So we are trying to just simulate that inorder traversal using indexes.
Right. Thanks. I will take a look. It's a very nice way.
Yeah.
Can we have the solution somewhere?
So this discussion, this one which I'm which we're discussing right now, it's part of the solution of the on the lead code problem.
Okay.
It's I think the third or fourth solution, or third or fourth approach for solving this problem.
Okay. Is it in the discussion part or the solution part?
Solution part.
Solution part. Okay.
Okay. If there are no questions on this, this problem, we can move ahead with the next one. Is that okay?
Yes.
Okay. So let's go to the last question for today, which is a hard one. Right. So the problem says you have a 2D grid of zeros and ones, right? And essentially what we have to find is we have to find the largest island that can be made in that grid. And what we have an option is changing one of those zeros to one. So at max, if there's a grid, we can change one of the 0 to 1. And what is the final maximum grid, maximum island that you can create out of it? Right. So let's suppose we have this 1 0 0 1. If I say here 1 0 0 and 1. So right now, if I set 1 is here, you'll see that there will be a largest island which is created of these 3 elements, right? If I place either here or here, it will be 3, right? The other example that they are saying is you already have 3 elements. There's only 1 0 and you set it to 1, you'll get all the 4 elements as 1, which is essentially a single island, right? And the case can be the already all 1 setup. So what will be the maximum island that you can make? So there's nothing to change. Already whatever is the maximum is what you can get, right? Okay. So essentially, and for the definition of island, what they're saying is an island is 4 directionally connected group of ones. That means if you have something like this, essentially everything on the right after the right diagonal is forming a island. Because somehow from the 4 diagonals they are connected. If this one is connected to the other one, and this is connected to the one which is on top. Does that make sense? Is the problem clear?
Yes.
Yeah, it is.
Okay. So any ideas? Let's discuss the approach and ideas about this one.
I think the simple brute force approach will be like start from each 0, whichever you get, and change it to 1, and then get the maximum length of island.
Okay, so let me share my screen and so let's say we have this 2D matrix. Right. So let's say we have some ones here.
Yeah.
Then zeros. Right. So what you're saying is
no pre-computation, no initial information, just whenever I get a 0, I change it to 1 and
right.
call a function which give me the maximum length of island in here. This
Okay, so
function
suppose
will
you take one
do the
here,
DFS. Yeah.
and then you
this
do a
function,
DFS, which will
yeah,
calculate everything from here till here,
yeah,
right?
yeah. I mean, it will calculate the length all islands and
Right.
give me the maximum value.
Okay, so for this one, suppose you found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you
Yeah,
have something like as max. Right now you have one max is 10, correct?
yeah. And then
Now
I
you
move
go
ahead.
here.
Yeah,
You again do the same thing. You set it to 1, right?
yeah,
Let's suppose this is 1, and you
yeah,
calculate this again area,
yeah,
and then you find again the number, which essentially in this case will be 9,
yeah,
right? And it is not maximum, so you not set it.
yeah,
And you will do this activity for all the nodes which
yeah,
are there, right?
yeah. And whatever maximum I had, I will also store the index. So later I will, if I need the information to return the index also, I mean, not for this question, but I can have that information also. The index
Okay.
information where I'm changing it to 1. The simple brute force I'm thinking, yeah.
So did you see something here? Like if I'm doing set 1 here, I'm trying to calculate everything here, right?
Yeah,
And then when I'm setting 1 here, I'm again trying to compare everything which I have already done, right? So
yeah,
this left part is getting calculated or traversed again and again.
again and again, yeah.
Is there a way we can reduce that?
I mean, something like I can pre-compute this information, like whatever, without even changing any bit, I will just have the information about my islands already. So if I change the left island to the very first 0, will have size of like 8, and the right island,
Sorry,
right side.
what you're
So
saying about what will you change there?
the very first 0 you have, right? The third, this one, yeah. So I will
Right.
get the island size on the left of it.
Okay.
Currently this is of size 8, right?
Right.
And there is a right island also, which is of size 2.
Correct.
And the island under it, 0, and island on top of it is 0.
Correct. So this is 0 and this is 0.
Yeah. So when I change this bit, I will just need to add those 2 island plus 1 more length.
Correct.
Right?
Okay.
Something like that may help. But
So you're saying how will you identify what is the size of this one? First step is that you have to calculate the size of this
Can
island.
we make any kind of a map or something where we can store the island's max value, that particular island?
Yeah. So how will you represent this map? That's what the question is.
yeah. So I need to
Let's
change
say
this value to island. I mean, any ij value can give me the island number to me.
Let's say this one is island 1, this one is island 2, this again is island 3, there's only 1, this is 4, and this is 5.
5. Yeah.
We can give any XYZ value to these islands, like.
Okay, and how will you know that whether this point is related to that XY?
Like all the islands, which like how the island problem we solve, like we find one particular island of this group, and
Right.
we gave them like something, an X island, a name to that
Right. So
island.
I understand what you're saying. My question here is, or the problem here is, the first time I'm here, I know this one on the left is giving a size of 8, suppose island 1.
Yeah.
So now suppose you're processing this one. How do you know this point belongs to island 1?
What we can do is we can store all the values, if like you have this island one and its size is 8, let's say. So we can store, we can make a new 2D array wherein we can store, like 8 everywhere for all the values. So whenever we'll be trying to if I put one adjacent to this island on any zeros, okay, on any
Right.
zero, if I replace any zero with one, so I could check if there is some non-zero number adjacent to the place where I had put my one. So if there exists some value like that, so what I can do is I can simply turn it to 9, and I'll get the maximum value like that, something like that.
Correct. So that's one of the approach that you're saying. So you can have a 2D matrix where you can store each index, I suppose 0, 1, 0, 2, 0, 3, and then say there's
No, no. What I'm saying is we can replicate the same matrix, and instead of storing 0 and 1, what I can do is I can store the island size.
let's say this one.
Yeah.
Then you have this much, and then you're saying it will be 8.
Yeah. So
Then
8 for
8.
all the places. Yeah. The whole island. In this way, for every discrete island we can store its number initially, its size initially. Sorry.
Okay.
Size
Uh,
But there can be another island which also has size 8.
yeah.
Yeah, that's not a problem. What I'm saying is, see, if suppose the size of island 2 is also 8. Okay, so you even write 8 here, there. So for the next time, if we put in the original matrix, if we put 1 somewhere in the third column, okay. So and I'll then check after putting 1 if there is any adjacent island to it. And if I get that, I can simply add it to the I mean, like, add the value to the same, and then I could update the whole island or something like that.
So what you're essentially saying is somehow find the group of islands,
Yeah.
and then in this new array or new 2D matrix, replace them with their length.
Yeah.
Right? Suppose we have these metrics which are giving the length as 8, 8, 8, 8, right?
Yeah. There could be some
And
other
now
island
what?
with any other
Yeah,
assignment.
let's assume we have 0 here, 0 here, 0, 2 here, 2 here, 0, 0. It's anything values,
Yeah.
any set of values. Now what? Not what will we do with this one?
Okay. Yeah. Now, if we check for all the zeros by replacing it by 1, okay. So suppose you take any zero and replace it by 1 for now.
Let's say replace it by 1.
Okay, yeah. So now I'll check if there is a non-zero number adjacent to this cell. Like
Okay,
I
so
have
there's a
here.
non-adjacent number. Yeah.
Yeah. So I could update this number, or I could keep a max number where I could store 8 plus 1. That will give me 9.
Okay.
Okay, for now I get that if I change this value, then I'll get a 9 as maximum.
Correct.
Similarly, I could go to other cell and then check and make it a maximum. This way, I
Right.
guess we'll.
Essentially, what you're doing is taking each zero and seeing what is on the 4 directions of it and trying to sum that up.
Yeah.
Right? That will give you what is the maximum size that you can do by replacing one of the zeros. Right?
Yeah.
So now this is fine. This approach is fine. Now my question is, do you really need this secondary array?
Puneet, 1 minute. Actually, this I will show why it will fail unless we actually put also the info that which island it belongs to. So in the same example, go to the 0, which will be there.
Sorry, Raju, I could not hear you. Could you please repeat?
Yeah. Can you go to the first 0 on the first row?
Okay.
And
This one?
yeah.
Okay.
And suppose my island was part of just below the 0, there is another 0. Make that guy 8.
Yeah.
Yeah, make it 8. And these islands are actually part of one island, So now when this guy will go to the left, it will add 8, right?
Right. It will become 16.
But that was the same island, so you are double counting. You understand where the problem lies here?
Yeah. So that's what I was saying. Like, instead of size, we should have a unique number or any other identifier.
With size, if you also add this as a pair, then it is good enough. Like, it's implementation detail, but you should store that.
So
in this
I think
approach.
what we can also do here is, as I was saying, to sum up all the four, just the four of its adjacent cells. We can check the other four as well. That will give us an idea somehow if it is the same island or the other island. So in that case, I think we can minimize our cost. I mean, sorry, not minimizing. We can minimize this error. We can counter this error. Hello?
I did not get what you are talking. So could you just repeat the?
Yeah. See, what we were doing here is what I was saying earlier was to sum up, to check all the four or all the four adjacent cells to the cell where we are changing it from 0 to 1. Okay, and then to sum that up. But Roger has come up with a brilliant, example where this method fails. So what I am saying is there are four more adjacent cells to the same cell where we are updating the value. Okay. Hi. Am I audible?
Yeah, go ahead. That's correct.
Yeah. So we can even check those cells and we can have a clear idea if the cells that we are adding are the same island or the different. In that way, I think we can keep track of.
But in third row, third column, if you see 0 there, right?
Yeah.
I will never able to understand like which 8 belong to the left side and which 8 belong to a different island, right?
What he meant was also checking these four directions.
Yeah.
Okay, got it. And then I
And
need to
checking
identify.
these four, I'll get an idea if that is the same island or the other one. In that way, I could come up with an idea to add whether to add or not.
The problem is by number you cannot conclude. You will always have some example which will break that. Most likely, it will be a good question to solve and suggest on that chat. Like, try that actually approach. I'm not sure. Maybe it will work, but not sure.
Yeah.
No, actually, it will either be related to this one or to this one, right?
Yeah.
In fact, if there's a non-zero number here, it has to be same as these two. Because by the definition, they will be forming a island.
Yeah.
Yeah.
But
so
we
if there's
can
a number other than. Yeah. Sorry.
Yeah, sorry. But we can simplify this by just maintaining this size information somewhere else and keeping it a different value, like island number 1 everywhere. Instead of 8, it will have a number like island number 99, island number 100.
For me, the one of the approaches is to use a disjoint set. So each island will become a disjoint set, and the root of that, or whatever is the identifier for that, will hold the total number of elements. Then if we have, let's assume this same case, where on the other side you have 8 here. What I need to check is just get from here, get the island number or the root identifier for this. Suppose I am calling it as 1. Then check for this one. If I've already calculated this one, I'll not go ahead and use that one again. I'll go for the other directions and check if there's another island number in my opposite vicinity, and then sum it up. Right? So each of these numbers can directly give me the island identifier. So if I am at this position, I'll know what island it is connected to and what is the size of that, right? Does it make sense?
Yeah, it does.
Right, so essentially, this is one of the intuitions that I usually have for the disjoint sets is if my data points are mutually exclusive and I just need one name or identify, like we earlier said, let's identify those with 1 or 2. This is my intuition that if I can use a disjoint set for this one. And then, of course, these points need to have some kind of relation, which is already given in the problem, right? Any other approach, anything else? Or any problems with this one?
I have a question. So while you're saying that all these are having a relation, so is it like we are storing all the data points of that particular island and giving them a particular ID? But like how?
So the disjoint sets or union find algorithm, they work in a different way. You have this parent array, okay, and you have it's not even an array. No, it can be array, it can be a map, something like that. You map each of them and store the parent of that. So or the identifier. So suppose there's an index called 0, 1, and I have all of this saved as a row major index, row major array instead of 2D. So this will become my index 1, right? This will become my index 2. This will become my 1, 2, 3, 4, 5, 6, 7, and thus, right? So for each of that, suppose 1, I'll put 1 as its identifier. And when I'm doing traversal, right? So as and when I move to some other, I can update its, parent identifier to what is a root identifier for what I have decided the root identifier till now. So everything 1, 2, 6, 7, they will all have identifiers 1. Right? Now every time I'm just looking at this one, I'll just calculate what is the index in the entire array, try to find what is the max, index or the identifier for the group. It's 1, right? So and I'll suppose I have another array which will just store, for index 1, size is 8. I'll just take it up and sum it up for this entry, right? I have 8 plus, if there's another 1, suppose the 1 is here also, 1 is here also. So this one will flow here also. You will have suppose 10 and 11 also pointing to the same root. I'll come here, I'll find what is the parent for this one, or identify this entire set. It will again give me 1, but I already counted 1 in my calculation. So it will not count again. Right? So it's the union find or the disjoint sets, they have a separate way of finding the optimal, not optimal, but the single identifier. And there are some optimization techniques also associated to that individually. So I would suggest take a look at that. That's it's a very easy to implement and very easily understandable way of identifying some set of data points which are related.
Okay.
Anything else, Roger? Do you want to add anything?
I have a question.
Yeah.
This huge parent array.
Sorry, I'm not able to actually hear you.
Hi.
Hello.
Am I audible?
Your voice is breaking. I don't know. Is it me only or everyone is having an issue?
It is breaking actually.
It is breaking.
Okay.
I think my internet is troubling. I don't know how to handle it.
Yeah, go ahead. It's better now. You can go ahead.
Okay. So what I was asking is it really necessary to maintain this huge array, the parent array, like you're written? Rather than this, could we do it something like we maintain a hash map, and therein, for example, we number these islands by 1, 2, 3, 4, 5, and in the hash map, the key is the number of the island, and the value is the weight of the island. So in that way,
Okay.
we could fill a newer array of ours with these distinct keys for each element, and whenever we'll be searching out, we could just sum up with the surrounding keys, something like that. The value of this.
How would you find that how would you find whether this index is actually associated to island number 1?
Okay.
You need some way to identify that also, right?
Yeah, for that we could maintain a new 2D array like we did in this case.
That is exactly what this parent is doing. It's just converted that 2D array into a single dimensional array, which is row major.
Okay, I got it. Thank you.
But you can, for simplicity, you can use this parent array as a 2D, If that gives you easier access or easier implementation for you, it's fine because the size of this array will be same. And if
Yeah.
you want to reduce that, instead of array, you can use suppose a lookup, which will just give you lookup from current index into the final identifier for that, right? It's
Yeah.
up to you. It may happen that the entire grid has only 2 ones and rest all is 0. So you don't want to, burden your parent array
Got
or
it.
parent lookup identifier, right? So it's essentially a lookup service or a lookup data structure, which will help you immediately identify what will be the identifier for this group where this index comes.
Yeah, got it. Thank you.
Yeah, the only thing I would like to add, that the problem we were trying to solve is like we go to a 0 and then 0 asks its neighbors, what is your size? And uh, it again asks the same question to other neighbors. We have to somehow identify that they are not talking about the same, they are not part of the same group basically, right? Because if that was not the problem, it's okay. But we got into that double counting problem. So union find by its very nature has that property that everybody just talks, lets the actually leader talk for him. So it will allow, hey, I don't know, let me ask my parent. And for each guys in a group, the parent is same. So they don't get into the trap of double counting. With DFS, what you could have done, actually mapping is one example. The other thing is you can change the value because now you only have 0 and 1 value. Suppose each island has its own value, say 2. Another island has all its value as 3. So, so just by mutating that, you can see if I see this my neighbor is 2, I actually know they are part of the same island. You understand what I'm saying?
Rather, that was the approach these were using, right? Instead of number, they were setting it up as
No, they
the
so
count.
they were they were just counting it, right? But yeah, it's similar to that. Like now you have that that value 2, and as long as you have a map that I'm my size is this one, you know that I'm part of that. Yes, so actually the same thing in a different way I was thinking, but yeah, essentially means the same. So the thing is union find, that is the difference. Like union find by its nature gives you, so you don't have to think about it. With DFS, we have no way unless we start storing that information, right? Because normally we just don't put that information in like a normal island problem, for example. We just count the size and we are done. So that's it actually. Not much.
May I ask a question? What's the complexity of the unified or DFS? Which one is better?
So both will have the same.
Okay, thank you.
Yeah, O of Mn, I think, because you will go to all the cell, and then even space, you will probably have, you will have O of Mn size. And then what he was saying, Puneet was suggesting that for the best complexity, if you're using union find, you should use path compression, and that will give you the best possible, that will give you actually O of Mn. If you don't do that, then it will be more than that.
Yeah. Thanks, Raja, for the explanation. Any other question or anything else that we want to discuss about this one? Okay. No. Probably then we can stop the session.
Yeah, thank you.
Okay. Thank you, everyone.
Thank you.